July 1st, 1940, a record-breaking suspension bridge opens to fanfare, its slender steel span hailed as a marvel of modern engineering. Yet as soon as it rises over Puget Sound, Galloping Gertie begins to shudder and sway, not from accident, but from an invisible, misunderstood force. What did engineers miss about wind and motion that turned a symbol of progress into a global cautionary tale? The answer would transform engineering forever if you know where to look. From the moment construction began in 1938, the Tacoma Narrows Bridge was shaped as much by economic pressure as by engineering ambition. The state's chief engineer, Clark Eldridge, pushed for a conventional design with deep, open trusses, heavy, stiff, and proven safe. But federal funds were scarce in the shadow of the Great Depression, and the Public Works Administration demanded a lower price tag. Leon Moisseiff, celebrated for his work on the Golden Gate Bridge, offered a bold alternative, a slender deck supported by shallow, solid steel plate girders only 8 feet deep. This cut the projected cost nearly in half, down to $6.4 million, and won the contract. Eldridge's warnings about flexibility were quietly sidelined. As the bridge took shape over Puget Sound, its narrow 39-foot roadway and graceful lines drew admiration. On July 1st, 1940, crowds gathered for the grand opening. The press hailed it as a triumph of modern design, the third longest suspension span in the world. Yet even before the first toll was collected, workers and engineers noticed something off. In mild winds, the deck would undulate up and down like a ribbon, sometimes rising and falling several feet. University of Washington engineer F. Bert Farquharson later recalled that they knew, from the night the bridge opened, that something was wrong. Locals called the bridge Galloping Gertie almost immediately. Drivers reported feeling their cars bounce as they crossed. School children begged for rides, eager for the thrill. Newspapers ran stories on the bridge's peculiar motion, and home movies captured the swaying deck. Some found it amusing, others unsettling. Attempts to solve the problem began quickly. Hydraulic jacks were installed as makeshift shock absorbers, but they failed to calm the movement. Later, engineers added tie-down cables to anchor the ends. On November 1st, 1940, a snapped cable showed even these fixes could not keep the center span steady. The spectacle of a bridge in constant motion drew national attention, but behind the fascination, a deeper uncertainty grew. Why did a structure built by leading experts, using the latest theories and federal oversight, move so much in ordinary winds? The answer, hidden in the interaction between AIR and steel, would prove far more elusive and dangerous than anyone had guessed. Wind on most bridges is a background force, steady, predictable, and accounted for in calculations. On the Tacoma Narrows Bridge, it became an active participant. The deck's unusual motion was not caused by resonance alone. Instead, the bridge fell victim to a more complex, and at the time poorly understood phenomenon known as flutter. Resonance occurs when an external force, like wind gusts or rhythmic loads, matches a structure's natural frequency. The effect is familiar: a child pumping their legs on a swing, or soldiers breaking step to avoid setting up dangerous vibrations. Engineers in the 1930s believed that as long as a bridge's natural frequencies stayed clear of common wind patterns, the structure would be safe. But the Tacoma Narrows Bridge revealed a deeper vulnerability. Aerodynamic flutter is self-excited. The bridge's own movement changed the way air flowed around it. As the shallow solid plate girders, just 8 feet deep, cut through the wind, air could not pass freely above and below the deck. Instead, flow separated and swirling vortices tugged at the structure. Each twist or dip of the deck altered pressure, feeding more energy back into the motion. The result was negative damping. Rather than dying out, each oscillation grew stronger, even in steady wind. This was not a matter of wind pushing in time with the bridge's rhythm. Above a certain threshold, around 35 miles per hour, The bridge's own flexing and twisting began to shape the very forces acting upon it. The H-girder geometry, chosen for cost and aesthetics, made the deck especially vulnerable. Its narrow width and shallow depth left it with little resistance to twisting. The solid girders, unlike open trusses, trapped wind and encouraged flow separation, making the deck prone to sudden and unpredictable shifts. No wind tunnel tests had been run on a full-scale model before construction. The science of aeroelasticity was still in its infancy. Engineers relied on static calculations and experience, unaware that the bridge's geometry had crossed a critical point where air and steel could interact in ways that defied expectation. The bridge became a feedback machine, each movement drawing in more energy from the wind until even minor gusts could set the entire span in motion. The difference between resonance and flutter is subtle but profound. Resonance needs a push at the right tempo. Flutter needs only motion and wind. It feeds on itself, unchecked, until the structure can no longer absorb the energy. For the Tacoma Narrows Bridge, this invisible force was embedded in its very shape, waiting for the right conditions to reveal itself. The lessons from these unseen forces would soon become impossible to ignore. At sunrise on November 7, 1940, a steady wind swept across the Tacoma Narrows, clocked at just over 40 miles per hour. The bridge's deck began its familiar, uneasy oscillation. First a gentle undulation, then sharper, more erratic waves. For 3 hours, the main span flexed up and down in a slow, relentless rhythm. By mid-morning, the vertical motion shifted. A loud snap echoed across the water as a mid-span hanger cable slipped loose. The balance was lost. The deck started to twist, one side rising as the other fell, swinging back and forth at a rate of 14 times per minute. On the bridge, Leonard Coatsworth's car shuddered violently. He tried to drive forward but lost control. Forced to abandon his vehicle, he crawled along the buckling roadway, leaving behind his Cocker Spaniel Tubby trapped inside. Nearby, photographer Barney Elliott set up his camera, capturing the deck's contortions as the wind funneled beneath and above the steel plates, feeding the motion instead of calming it. Professor F. Bert Farquharson watched from the shore, notebook in hand, as the bridge's movement grew wilder with each cycle. By 11 in the morning, the twisting reached its peak. The deck heaved nearly 28 feet from side to side. Suspender cables snapped in succession. Without warning, a 600-foot section of the center span tore free and plunged nearly 200 feet into the water below. The towers lurched inward, steel groaning under forces never anticipated. In just moments, the bridge that had stretched confidently across the Narrows was gone, leaving only swirling debris and stunned silence in its place. In the aftermath of the collapse, the Federal Works Agency appointed a panel of experts to uncover what had truly brought down the Tacoma Narrows Bridge. Among them was Theodore von Karman, one of the world's leading authorities on aerodynamics. The commission's investigation concluded that the bridge had failed not from resonance, as many believed, but from a phenomenon known as torsional flutter, a self-exciting instability where wind and structure feed energy into growing oscillations. This insight was more than an academic finding. It exposed a blind spot in the way engineers everywhere thought about large-span bridges. Wind tunnel testing, once considered optional, quickly became a standard requirement for suspension bridge design. Researchers at universities and government labs began building scale models to study how air moved over and around different deck shapes. The Commission's report was distributed to engineering societies across the United States and Europe, prompting revisions to design codes. The American Association of State Highway Officials integrated aerodynamic stability checks and damping requirements into its specifications. In the United Kingdom and Canada, similar reforms followed, with wind effects gaining new prominence in bridge planning. Tacoma's replacement, completed in 1950, reflected these lessons. Engineers chose an open truss design, allowing wind to pass through the deck rather than around it. The new bridge was tested in wind tunnels before construction began, a practice now considered essential. Engineering schools added the Tacoma Narrows collapse to their core curricula, using it to teach the difference between resonance and flutter, and the importance of dynamic analysis. Decades later, the story remains a touchstone for students and professionals alike. The failure of Galloping Gertie transformed a single disaster into a foundation for safer, more resilient bridges worldwide. Every major bridge built today faces wind tunnel tests because of what happened here. As our infrastructure grows taller and lighter, invisible forces remain a silent threat. The real danger is not what we see, but what we think we know. Failure keeps progress honest.